to do a quick walkthrough of the code and algorithms used in TempleOS. We'll start in the kernel, in the block device directory. This is for disks. Anyway, there's 3 file systems. I made a diagram. You have the Red C file system, the FAT32, and the ISO 9660. And Red C and FAT are for hard disks, and ISO 9660 is for CD-ROM DVDs. It's actually kind of old, but I'm not going to do the new ones. Anyway, so you can have ATA is for hard disks, a TAPI is for CD, DVDs, and then you can have RAM disks. A TAPI actually uses ATA commands. It's built on top of it. Anyway, so I want to talk about the allocation for Red C and FAT32. This is viewing the allocation bitmap for the drive, and this is kind of like what in the past you used to run check or scan disk or fix defrag. You used to defrag in the past. This is a bitmap for sector allocations. I'm obviously not using very much of the total disk space. With the FAT32, there's a pointer to the next allocated block. And what it does is it tries to cycle through the whole disk over and over, perhaps so you don't wear it out. I don't know. But one of the things that helped me a lot was somebody said, find the closest matching gap when you allocate. So for example, let's say you want, I'm going to zoom in. Let's say you have a file that is 5 blocks in size, and you're allocating space for it. What you try to do is find the closest to 5, and if you do that, it works a lot better than just allocating the first location. So what you do is you try to fit as close as possible. I don't know, it works pretty well in practice. I never stress my system. I never stress it. I always have a lot of extra room. Oh well. So the FAT has a level of indirection. It basically when you allocate a file, it tells it has a table, it has an array. So for block 0, the next block. So your directory might have a directory tells the cluster of the first block, and what you have is an array that points to the next block. And so this block, if we looked in the array, it would point to 3C, 3D, 3E, and the FAT system can have gaps. You could have a fragmented file if you wanted. When I made the Red C, it's just a bitmap, not FAT32 has an array of 32-bit. It has an array called the file allocation table, and so 0 might point to 1, 1 might point to 2, 2 might point to 3, and maybe 3 has a 0. Is it 0? I forgot what terminates it. Yeah, it might be FF. No, I think it's 0. I forgot. There is a FFF in the. Oh well. I should double check. Anyway, so so you have one file that's right here, and then you have you can have another file, and then this file, if you wanted to grow this file, you could replace this 0 with an 8. And now you just added a block to that file. And so that's how a fat table works. Anyway, so my Red C system just has a bitmap, and it only does contiguous. So on my Red C, you're not allowed to you're not allowed to grow your files. And but I do that trick where you find the closest for allocating, and it works pretty well. So there's a disk cache, and basically it's a hash table, and it's least recently used. Okay, let's see. There's a read cache. I don't do a write cache. I tried doing a write cache, and I had a problem because I hit a deadlock, and it was more trouble than it was worth. So I decided not to offer a write cache. So we want to look for the disk cache global variable. So there's blocks are 512 bytes, although there's some indication somebody wants to change it to more than 512 bytes. Some newer drives are starting to do that. Anyway, so the disk cache has a cache block. The cache block has a least recently used. It has a circular double link queue. So how could I draw this data structure? So there's an array of cache blocks. 0, 1. Anyway, so it keeps a list of least recently used, and when a block gets used, it gets bumped to the head of the queue. So the least recently used is the one that gets overwritten, and it's a hash table. When you're trying to find a block, you use the hash table links. There's a big array. Where is the array? I think. Well, here's the hash table. So that it's hashed by block number. So let's say you have 2,000 blocks. Maybe there's 100. Imagine an array of 100, and let's say you have 2,000 blocks and you have an array up to 99, and so if you have block 1 or 201, that hashes to 1. If you have block 400, that hashes to 0. All you do is take the last 2 digits. That's kind of how the hash works. Anyway, so when you have multiple partitions, you can have blocks with the same number. I think I might add the partition in order to scramble it a little bit. Hashing is just coming up with a scramble. Anyway, so there's a hash table when it wants to find a block, and that's how that works. And then it has the links for least recently used, so it knows which one to replace next. And then it has the block itself. These are not aligned. My hash table blocks are not aligned, which is so it's not on a 512 byte boundary. That's kind of ugly. I remember working with at Ticketmaster, their blocks were aligned. Oh well. Anyway, so there's a read cache, but not a write cache. And what other algorithms? When you do file names, it will convert a relative block or relative file name into an absolute, and so there's a string routine that will convert relative to absolute. A similar thing is also used in my help system. When you use the help system, it has you see these purple file. It's kind of like a directory tree. As a matter of fact, blocks or entries can be placed in multiple locations. Anyway, so I think that's all the disk algorithms. The keyboard and mouse have interrupt routines. If the mouse interrupt is not working, it will do polling, which is a lot of people have a false impression of polling. They think that it takes all the CPU. Well, I think I read the mouse, let's just say 50 times a second if the mouse interrupt's not working. And 50 times a second is not, it's polling, but it's not using up the whole CPU. A lot of people have a false impression. You can poll and not use up the whole CPU. Anyway, so when the keyboard routine is, when it's in the debugger, it doesn't use interrupts, and that's because you don't want things changing. A low-level debugger, you don't want it interrupt driven, or well, anyway. So what other algorithms? There's an LZW compression algorithm. I don't know if I want to explain this. Basically, the first, let's just say 256. It uses. I'm going to simplify this. Let's imagine you have 12 bits, and you have a table, and the dog went to the store. What an LZW does is it says, okay, I'm going to have a string T, and I'm going to have TH, and I'm a little bit confused, but when it hits this other TH, it has a pointer back to a previous entry, and so it's already seen this THE in the table. Oh no, actually it would have to be lowercase. Anyway, so what it does is it builds up strings, and it can point back to when it's seen before. So when you hit this point, it says, okay, start with THE space. And so now, so you tell it what string to start with, and so there's a string T, there's a string TH, there's I don't know if I'm doing this right, space. So the This one tells it to start with the THE, and then it adds one more letter. So each time it makes a new string in the table, it adds one more letter, and that's kind of how LZW works. And so what I did is for my file compression for my file system, if it has a Z, it automatically uses LZW when it reads and writes the file. If it has a Z on the file name, nobody else does that. Another interesting thing about my file system is if it doesn't find a file in a directory, it searches the parent directory, so that the parent directory can have default files. It used to be useful, but not when I had account files. Anyway, so I want to go over algorithms. So the display, this display code in here is for the black and white debugger. It doesn't have windows. Why don't we limit this discussion to stuff in the kernel? I'm not going to talk about the regular graphics, but anyway, so when you're dealing with it's tricky when you're in VGA mode. We're always in VGA mode, but the normal graphics routine updates the screen 30 times a second. When you're in this raw mode, I call this raw. What do I call it? I just call it raw. Anyway, it's raw, put char, raw, etc. So when you're in the raw mode, it has to copy bit plane memory. Anyway, you always keep a RAM buffer, and you don't work with the VGA memory the way. Okay, I'll explain that. Might as well. So VGA memory is I don't know if you can write it, but I don't think you can read it. So there's 4 bit planes. There's a plane for red, green, and blue, and then one for intensity. And what you do is, if you want to draw a red line, then you tell it to write to the red plane, and then you do the pixels 640 times y plus x. You want to index your pixel 640 divided by 8. There's 8 pixels per byte. So I don't know if I want to explain this. You have an array of bytes. It's a bitmap, and the order of the bits is not how you would like them. Anyway, so when you're doing the raw, it has to it's slow. Anyway. So the problem is when you want to write one character, it's not very convenient because you have to write to all 4 bit planes. So what I do for my graphics is I make a non-bit plane frame buffer that has all 4 bits together, and then I break the planes out, separating them. So in other words, normally you write to okay. Normally you set it to the red plane, then write the red bits. Then maybe if you want to make it red, you set all the ones that are red to 1. And then you set it to the green and set all the bits to 0. You set it to blue, set all the bits to 0. You set it to intensity, set all the bits to 0. And so here's the way it works. So you write to A00, and let's say you want to set some to red. They already are red. If you want to set it, they're white. Right now they have red, green, blue, and intensity set. So if you want to set them to red, you want the red FF, and then you want the rest of them set to 00. So this is, all of these examples are A. What is it? I'll do this pretty well. Okay. So in order to set, right now the screen is white and blue. Let's say you wanted to set these pixels to red, so you would leave the red. This is the red plane. This is the green plane. I don't know if I'm doing this right. I could double check. Blue, and then this is for, let's call it bright. Red is 4. Okay, I got it backward. So this is actually, blue is 1. Okay, so if we want to do this right, this is the blue plane, this is green, and this is the red plane. And when you want to set, let's set a color. Let's set the first byte to green. So we want FF there. We want 00 here. We don't want any blue present. We don't want any red. And we could leave it bright green. Okay, so that's how you set it to green. Now what I did for my graphics, I wasn't going to talk about this, but what I did is I went ahead and I changed it back into all 4 together. Anyway, long story short, or long story long. Anyway, so the display routine does black and white. I have a little editor. When you're in the what do we call it? The raw I/O mode. There's an emergency editor that is really simple. So there's an emergency editor, and what it has is a linked list of all the lines of text, and then or a circular link queue. So that means it makes a circle, and for each node in the circle, it's one line, and it's a line of characters. So that's how this little editor, that's all there is to this editor. And so there's a little editor. The fonts are a bitmap 8x8, and this relates to what we were talking about, the red, green, blue. I have an array. Normally, there's a text mode, B8000, and normally they do the ASCII and then the color, foreground, background. I have a text mode, or my text is 0 to 7 is the ASCII. I have the foreground, background. Then this is normally how the text mode works, but I extended mine to 32 bits, and you can actually do a superscript subscript. So if I want to subscript, okay, each character can be subscripted by up to 8 pixels. And then you want to change it back to superscript. So in my text array is subscript, superscript, and the Commodore 64 used to shift text around. You can actually do that anyway. So there's a blank, there's an invert, there's a select, and there's an underline. So I have an array for text, and then I use my 8x8 font for all the characters. So I have some, there's only a couple. This is like, you know, the standard template library has data types. I have a FIFO, and then I have a linked list, and I have a Q vector. Basically, if you want to add, if you want to grow an array gradually, you use the Q vector. The FIFO is implemented with the circular doubly linked, or not a circular. I'm sorry. The FIFO is implemented with the ring buffer. I think that's what you call it, right? Anyway, and I think it has to be powers of 2. I made dates, 64-bit dates. So at Ticketmaster, I learned it's nice if you have the day of the 32 bits for day since AD 0, and then 32 bits for time of day. So the if you want to know the resolution of we'd say 1. There are 24 hours in a day, there are 60 minutes, and there are 60 seconds. So I have a resolution of 50 thousandths of a second, and I use my 64-bit dates in my Red Sea file system. And if you want to know how many years I can do, so there's AD and BC. So AD and BC, and we have 365. We could get fancy. Let's just call it 365. So I wanted to do 4 billion so I could do dates since the birth of the universe, but or beginning of Earth. I don't have 4 billion. I have 5 million. Oh well. That's not very useful, is it? Oh well. So I have my first, what do they call it? Epic. I don't know what do you call it when the Unix time expires and the whole world falls apart? Kind of like the year 2000 bug. I have a year 2000 bug in 5 million years. So anyway, I did my own dates. They have, if you've ever wondered, I looked it up in, I don't know, Wikipedia or something, and you have your, every 100 years you don't have a leap year, but every 400 years you do have a leap year, but every 4,000 years you don't. So my, you can add and subtract dates. I don't store them as a structure. Anyway, it's very nice adding and subtracting dates. This is my debugger stuff. I have a string indirection table. When you make a pound define, watch this. I'm going to put so what I just did, if you hit Control T, there's a text entry looking for a pound define. I don't know. I used to call my company Trivial Solutions. So there's a string indirection table, and you can it's used anyway. So you can use it for multi-language text. Anyway, so if you say percent S, I think big S, and then you this is a printf, and you tell it company. You printed God. So you can do %s and then give a string indirection, a capital S. %S gives a string indirection. There's if you wanted to do months of the year in Spanish or English, you could use Z, and then you tell it anyway. So there's a string indirection available. I used to have all my text as for multilingual, but then I wanted just English, so I got rid of all that. So in this define direct file, I think it has the colors. It has some of the common lists. Interrupt names, colors, lock device. Okay, these you can define a list of strings. Anyway, so I have exceptions. My exceptions throw. You give it a 8-character string. So if we it's from my last video, kind of funny. Anyway, so if we make a say main, it just threw an exception. Oh, we never mind. Okay, so we have exceptions. Global variables, hash table. Do you know what a hash table is? Many people don't know what a hash table is. Go to F1. So there's an array of linked lists, and when you get a duplicate, so not only that, but if it doesn't find it in one hash table, it searches parent hash tables. There's a pointer to a parent, and so I use my hash. My hash table has a bit mask for or a type. So in my hash table, we have company, and that is a defined string. We have company, we have a duplicate, we have do it once, and we have main, our functions. So in one hash table, I have different types of entries. So if we said class, student, now if we look at our hash table has a class. So in one hash table, I have all these symbols, functions, defines. So there's a type, and you can limit it to just classes or just functions or just defines. There's a HTT, hash table type. So these are bits, they're not numbers. And so what you do is, let's say you wanted to search for a function or a type def. Actually, I got rid of type defs. Anyway, a global variable, or then you can make a bit mask, and it will do multiple. It'll search. It'll find either of those. So I have a hash table. I don't think you can remove. I think I might have gotten rid of the ability to remove. Maybe you can. I forgot. I guess so. We can hit F1. So you can use this for your own hash tables. I'm not a big fan of the standard template library. I like for everybody to make their own generally. I don't know. I don't like the standard template library. So hash table. This is a strange hash table because it has that 32-bit type. So it's not a very pretty general purpose hash table. I'm looking to see if you can remove. Yeah, remove and delete. Okay, well, those hash tables are just for my own system stuff. It's not like a standard template library. It is sort of. Anyway, so interrupts. I have faults. There's like the first 32 interrupts cause faults. Then I have keyboard, mouse, and timer is interrupt 0, and keyboard is 1, mouse is 12. Am I missing any? I don't remember. Anyway, so when you if you go to my website, you can get a file called binrep, and this will dump one of my binaries. There's only two binaries, kernel.bin and compiler.bin. So if I say binrep compiler.bin, so in my compiler are imports and exports. So these are all imports that are at certain these are all exports. So in my kernel I have a loader which will load a binary, but you're not supposed to use that. You're supposed to do just in time. There's just no reason for it. So I have a little bit of math in my kernel. I have support for some three-dimensional vectors, something like that. Random numbers and floor ceiling. I don't have that. This is supposed to be limited. You're not supposed to make it too. The kernel is not supposed to have the kitchen sink. Miscellaneous. So there's endian and little endian, big endian, and there's a sound routine. Anyway, so I could talk about the keyboard device thing. No. So I have I identity map all memory. So if you do a mem, this is what the BIOS tells me is physical memory. And what I do is I identity map. So what that means is I set all the virtual addresses equal to the physical. So I don't have a virtual allocator. I have just physical addresses. But I do have a malloc, obviously, and blocks. Each task is assigned is allocated. Each task allocates blocks of memory. Turns out I make my block size 512. That's kind of like when I was at Ticketmaster on the VAX. Basically, since I identity map, it doesn't matter what I do. I never touch the hardware memory pages. Once I identity map, mem-a during boot is called, and this identity maps. And then from then on, you can allocate blocks, or usually you just use malloc. So there's a I use the 32-bit call. Like, for example, if I say trace on, and then I say directory. At the command line, it compiled my directory command, and the directory command did a call, a 32-bit call, relative call. So this, on other operating systems, you have to do syscall or something like that, or software interrupts to change to kernel mode. Well, all my code is placed in the lowest 2 gig, and so all code can be is within 32 bits of a relative 32-bit call. Other 64-bit operating systems have a problem because when they want to do far distant beyond 32-bit addresses, then their calls get complicated or ugly. I put all my code in the lowest 32-bit or lowest 2 gig. So as a matter of fact, this chunk of RAM, the up to 7FFF is the lowest 2 gig. So that's my code heap. Everything else is the data heap. So if you go to the memory overview, so this is the low 640 down here. It has VGA memory, and then you hit my I have a fixed area. Then you hit my code heap, which is right here, and then everything else is the data heap. So let's say you have 12 gig on your machine. The lowest 2 gig is code heap, and then the rest is data heap. Anyway, I allocate a few data items off of the code heap. The task records are on the code heap, even though they're data. So your task addresses are 32-bit addresses. Anyway, so let's go back to the kernel. So my malloc is I start with a slab. Let's say I get 8 blocks of 512, and then your application starts allocating 100 bytes, and then 100 bytes, then 100 bytes. Then once it starts, it slices off the top of the slab, because that's a little bit, I don't know. Maybe I shouldn't do that. So my addresses start high and go low. So if you do a symbol numeric order, so this is a map of all the symbols based on numeric order, and the kernel goes in the low 640K. Here's the kernel in the low 640K. And then the compiler jumps way up high, up to 7F. Now it's allocating off of the code heap, going backward from off the top of a slab. So once it starts freeing, what it does is it puts them in when you start freeing, there's an array of let's say an array of I don't know, an array of 1024, and they're linked lists. So this is the 108 linked list, size 108. Then here's your 116, I guess. Maybe this one. Maybe you free a lot of 116s. And then when you reallocate, it just grabs it out of the array. Now it's compound, and so for bigger sizes, it's there's 512 pages. I think there's 128. I'm telling how malloc gets blocks, like 8 blocks, and then it starts mallocating off the top. So if I go to so my page tables are identity mapped, and that's at a location at 100,000, and then once you so it's a hash of 1024, and then we start using a bigger size. Anyway, so that's how my my malloc works. I tried the buddy system and it was too unstable. This will fragment because I'm using physical memory, not virtual, and the stack is limited to a fixed size of 128K. So when you identity map, it's not able to grow anything. Multi-core. So I use a round robin scheduler, which just means on each core it goes in a circle, and whatever task is ready it runs. And on the other cores we don't have any tasks. And when you make an 8-core flight simulator, your application spawns a task on these other cores, and you want to see that in action? How about let's do that. So I'm going to run. I don't know if this is going to work. So I want to Control Tab. Okay. Oh, I nuked it. Oh well. Did you see it? You want to do it? I won't do it again. Anyway, so there was a task on the other cores. Go back in the video and take a look. Pause it or something. Anyway, so my scheduler goes round robin. There are the task can be put asleep until a certain jiffy. My timer runs at 1,000 hertz no matter what. These are swaps. The timer is running at 1,000 hertz, and 1,000 hertz. Anyway, it goes round robin. A task can either be waiting for a wake up time or waiting for a message. And when you're at the command line, you're waiting for a key, and so it's asleep waiting for a key or a message. So this is kind of interesting. This video is getting kind of long. Anyway, psect. We have if I say unassemble, starting at, let's just grab an address. It's able to do symbolic debugging. That's because it scans the hash table, brute force. It's not designed to do this quickly. Anyway, so it scans the hash table for the nearest symbol, and that's how it's able to make symbolic debugging. But as it turns out, my my debugger only scans each task has a symbol table, and then the parent has a symbol table. And when you're doing symbolic debugging, it won't find a symbol in a sibling. It won't find a sibling symbol. So when you're debugging the window manager, it can be a problem. Here's the window manager. Anyway, so what it could do is not only scan parents, but scan siblings. I don't do that. We want to keep it simple. Anyway, so there's a on the wallpaper is it tells where each task is currently located, and that's done with my hash table. But what I do is I cache psect just to make it a little bit faster, because it actually takes a non-zero amount of time because it's not really designed to, psects aren't designed to be fast. So I have a cache. Now what that means is if you add a new symbol, when you're debugging, in theory you could have an error with an outdated symbol. I don't think that's ever going to happen, but it's not good with a debugger you can't trust. You can trust it. Anyway, QSort. So I have a built-in QSort. I'm not a fan of template libraries. So I have a special case QSort for 64-bit values. Normally, the standard, you have to enter the size of the each entry, but for my 64-bit, it's 64-bit values. It's just an efficiency. The nice thing is the callback for comparison is just 64-bit. It eliminates a level of indirection. So this 64-bit quicksort is nice. There's actually if you use the standard, it actually does 64-bit special case. Anyway, QSort. I pivot around. I think I do the midpoint so that if you do sorted lists, it's not bad. And oh well. As a matter of fact, I had an error not too long ago in my QSort, which was kind of embarrassing. Finally, I looked it up on I felt terrible looking up QSort on a Wikipedia or something. So my scheduler is round robin, and so you can. There's inter-process communication where you can tell a task. So the task address is 7F9D or D9. So there's inter-process communication. I can say do a directory. I can tell it a task. 7F D9 D228, and I'm going to tell it to do dir carriage return. Okay, so it just did a directory. So there's inter-process communication. You can tell it to do code. If you have a slave task, you can tell it a code address to start executing. If you hit F1, go to task. So the Atom task and the Seth tasks are executive server kind of tasks. So the Atom task is in a loop, and the Atom task is waiting for commands. The Seth task is waiting for commands. You can make a slave task that waits for commands. So at this moment, there's the Atom task. He's waiting for commands, as a matter of fact. I can tell Atom to print hello. And he printed hello. So he is kind of a slave executive. His memory will always be available. So if you're doing a let's say a wallpaper, you want to use I did it. Must be Atom included. Okay, so to do wallpaper, you have to Atom include, and now it's it's in Atom's code, so that it's not going to die. If I kill this task, we did not kill the wallpaper. That's because Atom owns it, and Atom never dies. So that's what the server command stuff. I have some string. I have a printf with extended codes and scanf. I don't really. In theory, you want when you print a string. In theory, you want it to always return. If you scan, you want it to be the same as print. But mine is kind of crude, and mine's efficient. My printf is very efficient. The way I do my floating point printf is what I do is I take what's on the left side, put it in a 64-bit value, and then print it out as a 64-bit integer, and then more or less I take what's on the other side, put it in a 64-bit, and print it as an integer. And so I can have overflows. Let's say you did %60f. We want a character turn. Okay, so it does that okay, but watch what happens if we say 30. Okay, it's not too bad. Be careful, because it will screw up in certain cases. Let's say you had this, and you wanted to print that. Well, let's do that. So instead of pi, we're printing this. Oh well, we get garbage. Let's say we have. I don't know what this is going to do. That worked. Okay, maybe it's not too bad. I was afraid it was really bad. Be aware. Anyway, don't use more digits than you need. Be cautious, because I think it'll screw up. Anyway, so we have extended codes, but so the big S is a string indirection for a pound define. We have you can print 20. You can print multiple single characters. Oh, capital character is big C. If you do big C, it does 2 upper. You can print multiple characters. If you want to print 20 blank lines, you can print a file with %F, big F. You can print a pointer. This is for source level debugging. I think everybody does that. Date and time, and then here's this is for list entries like days of the week. Then if you want to reverse a you saw when I was doing the atom stuff, I had to use backslash quotes. There's a oh well. If you say %Q and then you say \n, it printed \n or \tab. Okay, so it's anyway, when it reverses a %F, it reverses a printf. It reverses a printf. What was I saying? %F all along? Anyway, it reverses a printf. Anyway, so those are the algorithms in the kernel. How about we call it a day?